Okay, so just to let you know what we're going to do today, so I'm going to start with a quick recap for the benefit of those who don't remember what happened last week, haven't been here last week, were kind of lost last week. Then we're going to, so most of today we're going to go through the Coppersmith-Winograd paper from 87, but in a new form. So there have been two recent papers, one by Davy and Stollers from last year, and one by François Legal from last month. And now there's a reasonable exposition of all the details. So we're going to use their method, but we're basically going to go over this old paper. So after we do this warm-up identity, there will be some combinatorial construction and some open questions there. After that, we'll do the actual Coppersmith-Winograd identity. And then in the second hour, we'll do the squared identity. So if you've ever heard about identity squared, 4th power, 8th power, 16th power, 32nd power, and so on, then you'll get to know what all these means. And this will involve the notion of value, and there will be some proofs that I will skip. So it will be slightly less technical. And then I will explain how this identity might possibly be milked even more. This will be open question number 2, and we also have open question number 3, finding better identities. So we'll start with the recap. So omega is the exponent of matrix multiplication. So it's the infimum over all alpha such that n by n matrices can be multiplied in order n to the alpha. And I said that we don't expect this to be achieved. We also know, using the tools from last week, these tools can't achieve omega anyhow. But what we'll see today might possibly. Okay. So we developed this theory about, we found an equivalent way of representing this problem of finding the best matrix multiplication exponent, and it involved tensor rank of matrix multiplication tensors. So here is a matrix multiplication tensor. Okay, so it represents multiplying an n by n matrix by an m by p matrix, resulting in an n by p matrix. So this is this n by m matrix, this is the m by p matrix, and this is this n by p matrix. And this tensor, so there's this notion of rank decomposition. So you write this tensor as a sum of rank 1 tensors. And this is the same as this class of bilinear algorithms that we proved last week that they're the most general form of matrix multiplication algorithms with the result of Strassen. So really, the exponent of matrix multiplication is the same as the exponent of the rank of matrix multiplication tensors. But you don't actually have to know that. Because really, all the developments in this theory, the idea is, suppose I have some kind of bound on some kind of rank of some tensor. How does this give me a bound on omega? So we started with some simple things. So Strassen's algorithm showed that, well, n to the omega is at most the rank of the matrix multiplication tensor n and n. And then the next step in the line was if we have something which is not cube. So we had this. And then there was this notion of border rank, which is maybe your tensor has high rank, but it can be approached via a sequence of tensors of lower rank converging to it. This is something that can't happen for matrices, but it can happen for tensors. So this notion of border rank, we, well, you denote it like this, and everything works also for tensor, for this border rank.
Did you check, by the way, what is the largest gap now between border rank and rank?
No, and I imagine even for 3 by 3 matrix multiplication.
We know that it can be 1, but do we know that it can be bigger?
Yeah, I didn't check. Oh, but something interesting, it's possible to compute the variety of border rank tensors, of tensors of given border rank. So when you want to prove lower bound on border rank, then in principle, if you've been here for if you attended Josh's talk, then all the tensors of border rank is no something, they form a variety. There's some, so you can write a system of polynomials, and their common zero is exactly these tensors, and there's now a method of actually doing this, carrying it through. So if you're interested in lower bounds, you can talk to me later. Okay, so we have these two easy things, and now we have the combination of the classical theory of matrix simplification. This is the asymptotic sum inequality. So this is this thing. Okay, so what's happening here? Here we have the direct sum of several different matrix multiplication tensors. Now what is direct sum? It just means that these tensors have disjoint supports. Okay? So you can think of it as a direct sum of matrices like a block matrix. So it's the same idea. So this is some way of multiplying several matrices of different dimensions, possibly. And this gives us the best bound of omega that we can get from such an identity. And I'll prefer writing it in a slightly different way. Maybe I'll keep that. So the asymptotic sum inequality so suppose sum I of ni, mi, pi to the alpha over 3 is at most this border rank of this big disjoint sum. Then omega is most alpha. So this is equivalent. And what was the idea of the proof of this asymptotic sum inequality? So first of all, if we are in a situation where all these tensors have the same dimensions, and let's say they're all cube, then it's just the same kind of idea with Strassen algorithm. You do things recursively, and you amortize. So this is the idea. And more generally, you take this tensor, and now you take a high tensor power, and you isolate the best type of tensor that is there, and you just apply this amortized algorithm. This idea we're also going to apply it today, but to a slightly more general problem.
It's like typical sequence code.
Yes and no, because you also care about how much this specific tensors are worth to you. So it's not really the most common one, but you also have to weight them. But yeah, if you also weight them, then it's fine. Okay, so now today we're going to extend these methods to handle the case where these basic tensors in our identity are not disjoint. Hey, this is Strassen's laser method. There's some explanation in the book why it's called the laser method, but we'll not get into that. So now you can already take a look at your notes. This came much quicker than last time. So we're going to start with this warm-up identity. So this is already the Coppersmith-Winograd paper from '87. So you can look at the identity, and here I'm summarizing it. So no, so I'm going to explain it now. Yeah, so what's happening here? So what are the variables that are involved? So the x variables, we have this guy, and we have these guys. I can say q is just a parameter, in case you're wondering. We're going to choose a q equals 8. And we have these y variables and these z variables, same thing. And you see here the superscripts. And the superscript is a way to indicate a partition of the variables into groups. And why is this helpful? So I have here all these matrix multiplication tensors, but they're not over disjoint variables. But I want to say which of the variables they share and which are disjoint. So here, this tensor, the x variables come from 0, and the y and z variables come from 1, and so on. Okay?
But y and z variables come from 1, but we have q of...
Yeah, but this is an inner product of size q, so we use all of them. So this is, so we were multiplying, computing this, we're computing the inner product of these two vectors, y1 and z1, and putting the result in x0. So in some sort, this is a very trivial identity because we're only computing inner products, which sounds much easier than multiplying matrices.
Yeah, but you're doing 3 inner products.
Yeah. And I can also say, so there's here an inequality, but this is probably an equality because this identity can be used to do optimal rectangular matrix multiplication. And I think this indicates that it actually has to be optimal, this q plus 2. Of course, it has to be at least q. Yeah. OK. So now what's the idea here? How do we handle this mess? So it's exactly the same thing. We're going to take a high tensor power, and we're going to zero some variables. And now we're going to do it in such a way that whatever remains is actually disjoint. And then we're going to apply the asymptotic sum inequality. Okay, so this is this laser method. And the thing which is not clear is how exactly to do that. Okay, so let's see what happens when we take, say, the square. So this is the same as squaring the basic identity that we'll do in the next hour, only simpler. So when we square this identity, then we get something like, so we get 9 terms here. This is at most q plus 2 squared. Now, what do these terms look like? So for example, one of them, it's 1, 1q times q1, 1. So this is a bit implementation that we also used last time. This is a tensor product. So this is like the conical product of matrices. OK, and we know if we didn't care about the names of the variables, then this is just a tensor of shape q1q. So now it's an outer product. And I can add the annotations of the variables. So this means that the x variables are of type 0, 1, and the y variables of type 1, 0, and the z variables are of type 1, 1. OK, and we can continue this way. Now, yeah?
Sorry, is this identity obvious, or are you going to prove it?
It's in your handout. No, this is an excellent question. I don't know. I don't remember what they write in the paper. It's obvious to verify. Yeah, NP obvious. Yeah, so in general, if we take the 100th tensor power, then this part is easy to understand. So we can say what are the index triples that occur. But with the dimensions, it's also possible to understand. But actually, we don't really care. All we care about the tensor is this quantity NIMIPI cube root. So we will call this the volume of a tensor. And we will use the letter V. And in the next hour, we will call, there will be another thing using the same letter, which we call value, and has the same value for these tensors. So you'll see like things will look familiar. Yeah, so all these 9 terms, or in general, well, if we take the nth terms apart, then we have 3 to the n terms. And all terms have volume q to the n over 3. So again, volume is just NIMIPI cube root. Okay, so they all have the same volume. So we don't have to care about the actual, it's called formass. Yeah, so here volume, it's, I'm taking the cube root of the product of the dimensions. Yeah. Yeah, the actual volume is,
The actual volume is q to the n.
yeah, so Yeah. Right. Yeah. So we don't care about the format of the actual tensors. We just care about how many of them we can keep together. So now the problem is that. So you consider this set of index triples. So it's 0, 1, 1, and 1, 0, 1, and 1, 1, 0 to the n. We want to, yeah. So now it's going to be the set of index triples of length n, where they come from this construction.
Okay, so there should be another plus.
Oh, sorry. Yeah. Right. That's a typo. So we want to, the goal is to zero variables, or we're really going to zero sort of types of variables. So we're going to zero indices. So we zero indices. And we have to zero the x indices, y indices, and z indices separately. So zero indices such that all triples that remain are disjoint. So what does disjoint mean here? So it means that there's no x index that repeats, and no y index that repeats, and no z index that repeats. And that ensures that the actual variables are all actually disjoint. Okay, and we want to get as many of them. So suppose we can get Kn. Then the asymptotic sum inequality shows that so Kn times q to the n over 3 is at most q plus 2 to the n. And now we take in an nth root, so we get, oh, there's an omega here. Kn to the 1 over n times q to omega over 3 is at most q plus 2. Okay, so we're really interested in this, the limit of this quantity. Okay, and once we find a good bound for it, then this will give us a bound on omega. We'll have to optimize over q also, but I can tell you it's q equals 8, I think, in this case. And this will give us the bound. Okay, so now it's a purely combinatorial problem.
It is strange that it's not monotone in Q. It seems that this inequality, the basic inequality written there, seems like, you know, if you can do it for larger and larger, you should have Q more. So I guess it's a zeroing that forces.
No, even before the zeroing, even last week there were a few identities like this. I didn't present them this way, but they actually had even 2 parameters. And then you needed to optimize over 2 parameters, and there was some unique choice that was the best. It's hard to say exactly why. I mean, maybe you can think of this parameter as being continuous, and then it's very natural for it to have an optimum.
No, it just seems that this inequality there is more impressive the larger Q is, right?
Right.
Because the obvious upper bound is 3Q, and you get Q plus 2. So the gap, I don't know.
Yeah, but this is all very mysterious. Okay, so do you understand what we're trying to do? It's very important. Okay, so now what I'm going to do is I'm going to present 2 really trivial upper bounds on this quantity Kn, and then we're going to show that we can actually get this upper bound. It's going to be very surprising. And for the construction, we'll do it in more generality, so that we can apply it for the other identities, and also there's an open problem there. Okay, so I'll have to erase this. Okay, now the upper bounds, they come from the paper of Cohen, Kleinberg, Segedi, and Ullmans. It seems that other people didn't care about trying to optimize this construction. But it's very easy, so, well, you'll see. So how big can Kn be? So the bound 1, Kn is at most 2 to the n. Does anyone see why?
Because otherwise you get the same, if you have more than 2 to the n, you get the same, you have 2
Index.
adjacent things on the Q.
Right. So after we zero the variables and we look at all the triples, then all the x indices must be distinct. But how many x indices are there? There are 2 to the n. Because each position can be either 0 or 1. Okay, so this is a very trivial upper bound. And now we're going to do something slightly more sophisticated. So for each of these index triples of length n, we can look at its provenance. How many of each basic type we took to construct it. So we say that ijk has type ABC if it came. Yeah, I is a binary string of length n. Yeah, exactly. If it came from A, whatever, 0, 1, 1s, B, 1, 0, 1s, and C, 1, 1, 0s. Right. Right, and this also implies that there are only polynomially many different types. So now, without loss of generality, A is at most n over 3. Otherwise, we'll pick one of the other guys. So there are at most n choose A triples of this type. Now, why is that? So if you look only at the x indices, then there are A which are 0 and n minus A which are 1. So there are only n choose A different possible x indices. Yeah, and we can always choose one of them, either A, B, or C, which is at most n over 3. So we got this bound n choose n over 3. So in total, it implies that Kn is at most n squared, there's some constant here, times n choose n over 3. And this is roughly 2 to the nh of 1/3. Okay, so as you take the nth root, then you're going to get 2 to the h of 1/3. H is the binary entropy function. Okay, so this is what we will call the trivial upper bound. And rather surprisingly, you can actually achieve this upper bound.
So you take them all equal to n over 3.
Yeah. And in the future, we'll have to optimize over this as well, because the situation will be more general. Okay, so is the upper bound making people happy, entertained? Okay, so now the construction, and this is really the surprising bit. So we'll do it in more generality. So the parameters for the construction so one is a list of basic triples. So in this case, it's this 0, 1, 1, 1, 0, 1, and 1, 1, 0. Okay, and this list has to satisfy 2 constraints. So one has to be rotation invariant. And 2, it has to be tight. So all indices sum to a constant. Okay, so what does rotation invariant mean? It means what you think. And this is for reasons of symmetry. Everything will be much simpler. Maybe you can do it without the symmetry. And B, and this is, well, you'll see it comes out from the construction. It has to be tight. So all of these numbers, 0, 1, 1, 1, 0, 1, 1, 1, 0, have to sign to the same thing. Of course, in this case, it's trivial because we only took one of them and took all these rotations.
Well, what do you mean sum?
So we want 0 plus 1 plus 1. This is equal to 2. And we also want 1 plus 0 plus 1 equal to 2.
So rotation invariant, so isn't the sum always
No, because here there's only one basic type and we take all rotations, but there may be more.
It can be more than.
Yeah. And you can think during the break of an example where if you have lots of rotation invariant basic triples which are not tied, then there's no possible way of mixing them together. Okay, and 2, we want a source distribution, pi, over the basic triples. So in this case, pi is equal to 1/3, 1/3, 1/3. So what's happening here? So in general, there will be more basic triples, and each of the basic tensors or whatever will be worth something different to us, potentially. So we really want to look at things in the tensor power that come from a specific distribution, because the volume is going to be different. So this is the volume of tensors we're going to look at in this case. We take 1/3 exactly of each. Now, if you're very pedantic, then you'll notice that sometimes n/3 is not an integer. And more generally, the values here could be, irrational. But let's not worry about it.
But in general, you are looking for an independent set in a weighted big graph.
Unfortunately, no. It's more complicated. We'll see why. Yeah. So now, how are we going to evaluate the construction? So we're going to define some parameters. Well, maybe before that. So now the goal is going to be the same. So we have this. We take some. Well, we get some n, capital N. So given n. And we're going to look at this nth power, and we're going to 0 variables, and whatever remains has to have distinct x indices, y indices, and z indices. And then we want to count the number of triples of this type. Okay, there might be triples of some other types, but we don't care about them. We're only interested in triples of this type. Okay. So given n, we define the following quantities. So f is the number of triples of type n times pi. Okay. P is the number of x indices of type n pi. So an x index is of type n pi if it occurs in some triple of type n pi. Okay, so in this case, well, this is n choose n/3, 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 and here it's n choose n/3. Okay, and we'll have G, which is the number of triples of projection type n pi. Now, one is a triple of projection type n pi if all its indices are of type n pi. So if you look at the x index, it could have come from a triple of type n pi, and the y index could have come from a triple of y n pi, and the z index also. And it's kind of hard to concoct a situation where these two things are not the same. But it actually happens. But here, they're just the same. So here, if a triple is of projection type pi, it's actually also of type pi. But in more general situations, it's unfortunately not the case, and this is related to open question number 1.
Does really matter? I mean, f after all is more or less 3 to the n, or whatever.
No, yeah.
To the n.
Yeah, sure.
There will be always a polynomial number of parts.
Yeah.
So, and since we are taking n roots, okay. So this is, we can think of this as just n power.
Sure. Yeah, that's true.
And the same holds for 3, for G.
Yeah, and we'll actually see that when we come to the optimization problems that you need to solve.
So even if they are not the same, they are more or less the same.
No, they're definitely not. No, they can be different. So here, here the situation was kind of trivial because this is the central coefficient, but it doesn't have to be if there are more types. This is actually some kind of mess, which we'll get to. Okay, so now the trivial upper bound shows that Kn is at most P. Okay, and what we're going to give, construction gives f over g times p to the 1 minus little of 1.
Okay.
Yeah, so Kn is at least, it's this thing, and it's, yeah, it's at most P. Okay, so do you understand what we're trying to do here? Okay, so now we're going to start with the mock construction, which is this independent set type construction. Then we're going to, so the goal is going to be a bit different, and then we're going to do the actual construction, and you see where we get stuck. And then to get unstuck, we use this, this really weird combinatorics, this Salem-Spencer sets and all sorts of weird stuff. And I'll comment why this is actually not needed. It's still nice. Okay, so the mock construction. So here the goal is choose triples that are disjoint. All right, so instead of zeroing variables, now we're going to just choose triples. Okay, and everything is going to be very easy. And of course, if you can choose triples, then you can focus only on triples of actual type n pi, and then you expect to get this p to the 1 minus little of 1. But we're actually going to get p over 12. Okay, so what do we do here? So the idea is very easy. It's very simple. So idea. So you choose each triple with some probability epsilon that we'll optimize over. Now say a bad triple is a chosen triple that conflicts with another chosen triple. Right. And a good triple is the one which is chosen and not bad. Yeah, so I'm throwing all the bad triples, and we're going to take everything that remains, and this is all going to work. It's all going to work out. Yeah, so let's see. So the probability that the triple is chosen so what's the probability that the triple is chosen in the first step? Yeah, it's a trick question. It's epsilon. So it's just by definition. So now the probability that the triple is bad, to understand this, we need to understand the possible conflicts. So what does the conflict look like? So it looks like this. So this is your chosen triple, and this is another chosen triple with the same I index, say. So how many of these triples are there? So in total, there are f triples. And if you project to the first coordinate, then there are p different x indices. And everything is symmetric. So I'm saying that the number of potential conflicts is just f over p minus 1. Okay, so f is the total number of triples, and if we bucket, well, there are p choices for the first coordinate. So if you look at how many have this first coordinate, it has to be f over p. Okay, so now the probability that a triple is bad, it's at most epsilon squared times f over p. So the probability, well, 3 times. There's 3 indices. So the probability that a triple is good is at least epsilon minus epsilon squared times 3f over p. Now you optimize over epsilon. So you choose epsilon equal to p over 6f. So this probability is equal to p over 12f. So the expected number of good triples is P over 12. Yeah, and this is exactly this independent set construction. Yeah. Okay, so far so good. Now let's try to see what goes strange when you try to do it for the actual problem we have.
I'm a little worried that only I'm asking questions, so we want to ask if everything is clear.
Yeah. Which point did you find hardest to understand? Are you engaged? Okay, you can watch the video again. Everything will be much clearer. Okay, so now the actual problem, we don't choose triples, we choose variables. So the way that
This is not good enough.
no, because this is not the actual problem. Because in our problem, we were zeroing variables. Yeah, it was very confusing. For a few months, I thought that this construction should work, and it actually solves this conundrum with the f and g, until I understood that it actually doesn't. So yeah, no, I'm explaining exactly right now. So here we were choosing triples, but in fact we're choosing variables. That's what we want to do. So given the triples, you can choose the variables that appear in the triples. But then there's one bad thing that can happen. So suppose you chose this triples. So this is, there are 3 triples in your list. No, you choose variables. You zero indices, and this chooses some triples, but it's in a very specific way. It's only the triples that you haven't zeroed their indices. Yeah, you choose triples, but you can't choose any subset of the triples that you want. No, because you're choosing them by choosing the sets of indices. So you choose a set of x indices, or y indices, and z indices, looking at all the triples that satisfy these constraints. So you can try to do it the other way. You have some triples in mind, and now you zero all the variables that don't appear in them. Yeah, so these are 3 triples in your list that you chose, and now it could be that this is another triple. But together there's an ensemble, like a conflicting ensemble. Okay, now, so these ones have type n pi. Right, that's how we chose them.
So I1, J2, and K3 is another triple, another basic triple.
No, so this is a triple of length n. All of them are triples of length n. Now you made this list of triples this way, and now your idea is you're going to zero all the variables that don't occur in your list. But your list is incomplete because there might be other triples which survive this process. For example, this triple. And this triple has in general projection type n pi, so it doesn't need to have type n pi, because all we know about it is that the x index has type n pi and y index and z index. Yeah, and this is all the mess. So now one thing you can, so first, do you all understand the problem, the issue? No. So what we're doing is so you look at your list, and now you make a set I of all the indices that appear here, and a set j of all the indices that appear here, and k all the indices that appear here. And now the surviving triples are actually those that have their I indexes in the set I, j index in the set j, and k index in the set k. Well, it's the intersection of, yeah. It's not quite a product set because it also has to come from your basic triples. So the intersection of, yeah.
So you want to kill I1, J2, K3, you want to kill this triple?
Yeah, and the only way to kill that is really, right. That's not good. Yeah, that's a problem. Yeah. But one way to address this is to say, okay, so if we are in this situation, let's forget about this triple I1, J1, K1. Okay, and this will fix everything. So what happens when we do that? So we had another clause to when a triple is bad. So let's see what we get. So suppose I have this triple, and I want to see how many possible conflicts it has. So how many ensembles of this form have a given I1, J1, K1? So first, to choose this triple, I have G over P choices. Okay, and to choose, so now I have this is chosen, this is chosen. And to choose this triple, now I have f over p. And to choose the final triple, I have another f over p. Okay, so these are the number of potential conflicts. And each of them happens with probability epsilon cubed. Okay? And now you can do the same optimization, and you'll get some value for the probability that the triple is good. And you'll get some value for the number of good triples. Now, in our specific case, so if you carry this out, then you get roughly 2 to the n times log 3 minus 1 triples. But you wanted to get p, which is 2 to the n over log 3 minus 2/3 triples. Okay, so this is a good construction. It's just not, we can do better. Okay, and the way we do better is very kind of odd. Okay, so this idea works. We can do the same thing. It's not optimal. Yeah, so now we have another idea. So the other idea is to choose the triples in such a way that if all these 3 lines are chosen, then suddenly also the yellow thing is chosen. So if we ensure that, the triples don't conflict, then this type of thing just can't happen. Okay? So this is the idea. So we choose the triples so that if the triples in the nth tensor power, so that if all white triples are chosen, and so is the yellow one, and chosen triples don't conflict. Okay, and then
say that if whites are chosen, then yellow are also.
Yeah.
Does this mean that you get a product set intersected with them?
Well, we always have a product set because that's so we get the intersection of the product set I times j times k and this n to the power. Yeah. So how do we do that? So we come up with 3 hash functions. hx, hy, and hz from the, so in this case, they're from 0, 1 to the, well, say sigma to the n to some zm. We're going to choose m later, and it's going to be prime. And a set A in Zm of size n to the 1 minus the of 1. And we choose an index if the hash of the x, y, or z is in A. Okay, and then we have this property, because if the hash of I1 is in A, and the hash of J2 is in A, and the hash of K3 is in A, which is the case if all of them are chosen, then also the other one is chosen. Okay, so yeah, so this is the idea. And now what is entirely unclear is how do we do this choice in a dependent enough manner so that you actually get a lot of triples. Yeah, that's the thing which is not so clear. Yeah, so we have 3 properties satisfied by the hashes. So one is So if so for any triple ijk, if any two of hs of I, hy of j, instead of k are equal, then all are. Property number 2. So if all, so we look at the 3 hashes, and I'm saying it can't be that exactly 2 of them are equal. Now, second property is so for all triples ijk. So this condition that we choose.
Similar to the triple product property in the group construction.
The triple product property is exactly what we want here. This is exactly the same. Well, sort of. If you look at they don't take the Janssen power, but yeah. So we have, so this triple is chosen if and only if they're all equal. This is the really surprising property. So the condition that each individual index hashes to something in A is the same as requiring all of them to be equal and hash to something in A. And this is the kind of dependence that is going to save us.
Yeah, but it depends on the structure of A matrix.
Yeah, yeah. That's where these, yeah, we'll see. And 3, so for all triples I, j, k, and I, j prime, k prime, then hx of I, hy of j, and hy of j prime are uniform over that m cubed. So if you look at them this way, then they are sort of 3-wise independent. Okay, and given these properties, the construction is very simple. So maybe okay, so now the idea is exactly the same. So you define a triple is bad if it is chosen and conflicts with a chosen triple. Is good if it's not bad, and it's also chosen. And now, if we look at only the good triples, then they're going to satisfy all the properties. So we just need to estimate the probability, the number of good triples. So what's the probability that a triple ijk of type n pi is chosen? So when is a triple chosen? If all the indices hash to some value in A. But actually, it's the same as asking if for some value in A, all of them hash to the same thing. So it's so the size of A. Now we don't have to look at 3 of them. It's enough to look at 2 of them. This is because of property 1. And then because of property 3, it's exactly this thing. Which is m to the minus 1 minus a low of 1. Now, probability that ijk is bad. So again, we have, so what's a conflict now? So a conflict is something like this. Okay, and there are G over P of this type, and in general, there are 3G over P. So now, again, what's the probability that both of them are chosen? So in order for both of them to be chosen, then suppose that this hashes to some value a, then this must also hash to a, and this must also hash to a. Right? So this happens with probability m to the minus 3 times g over p, which is m to the minus 2 minus of 1 g over p. Okay? And now it shouldn't be so surprising. This is very similar to what we got last time, but now instead of f over p, we get g over p. Okay, so you do the calculation, and you get that the expected number of good triples is, so it's f times g over p, sorry, times p over g to the 1 minus little of 1, which is what we wanted. Okay, so why do we get a discrepancy between f and g? So the potential triples that we want, there are f of them, but the potential conflicts, there are g of them. So that's where we get this difference. Okay, so now all I have to do is I have to tell you how we construct these. Yeah, so we're going to choose m to be roughly p over g. Sorry, roughly g over p. And then when you do the math, then you get this. Yeah, so m is going to be roughly g over p over some constant. Here there's also 3. Okay, so now, any more questions about this first? So now all we have to do is to construct this, these hash functions. And this is going to be surprisingly simple and surprisingly tricky at the same time. So constructing the hash functions. So before we do that, here we assume that all the basic triples are tight. So the sum is constant. But now we assume that the sum is not only constant, it's also 0. It doesn't really matter. This will make things a bit simpler. Okay, so we choose alpha from Zm randomly, and then alpha x, alpha y, alpha z from Zm randomly under the constraint that they're all summed to 0. Okay, and now hx is going to equal to twice the inner product of hx of I. Of alpha with I, well, I guess, alpha with I plus alpha x. Hy of I is equal to twice alpha in j plus alpha y, and hz of k is going to equal minus alpha k plus alpha z. And you'll see in a bit why these funny coefficients. Yeah. Yeah. So now what's happening here? So because so we have the property that for every triple, this sum is just a 0 vector. And because every basic triple, we're saying is going to sum to 0. And this implies that hx of I plus hy of j is equal to 2hz of k. Okay, so that already implies property 1. So if 2 of these y's are equal, then the third one is also equal. And you also get property 3 because of the way we constructed it. So it's sort of easy to see. So now we just have to construct this set A so that this is satisfied. So now what is the property that we need of A? So we want if hx of I and hy of j and hk of hz of k are in A. This is if and only if they are equal, and in A. So what is this thing saying? It says that there are no non-trivial arithmetic progressions of length 3 in the set A. Okay, and very luckily, I think the first people who constructed this were Salem and Spencer. And since then, there have been many other constructions. For us, these other constructions, they don't make any difference because all of them get this m to the 1 minus the log of 1. Yeah, so we're very lucky, and someone actually constructed this at A for us. And I can say the construction is pretty simple. The paper is 2 pages. It's not so, you can do it really in hands-on. Yeah, so this is the entire construction. Okay, so further questions about that? Who's still following? But if nobody's following, then I don't have to do the second hour. Yeah, so now there are 2 comments about this construction. So the first comment, here we were using these Salem-Spencer sets, but in fact you can get rid of them. If instead of zeroing variables, you allow yourself to this more general process of degeneration, which is you attach to each variable some power of epsilon, and then in the end you only look at whatever remains with the lowest power of epsilon. So this corresponds to what we did with border rank. So if you do this, then you can do a direct construction, which is much simpler than a Salem-Spencer construction. So if you want, it's in my lecture notes or in the book. It's some construction by Strassen. So we don't really need these Salem-Spencer sets. That's part of open question number 1. Yeah, it's more general because it also zeroes variables. So it zeroes variables, and it also does this degeneration. OK, so now open question number 1. So we see here an upper bound and a lower bound. And in general, they're not the same. So which one is true? Since there was so much effort on doing the lower bound and the upper bound was kind of trivial, then I imagine you can tighten the upper bound. But I haven't been able to do this. So this is the first part of open question number 1. Find the correct answer here. We're only interested really in this limit of kn to the 1 over n. And part 2, in case, so it might be that this Strassen type construction can actually get you better things than this construction. So if so, it will also be interesting to know. OK, now we will very quickly, just before the break, do the basic Coppersmith-Winograd identity. Given everything that we did so far, there's almost nothing we need to do. So you can look at your handout at section number 2. So now we can see another identity. It has the same border rank q plus 2, but now there are 6 terms in the left-hand side. So there was somehow a way of adding more terms without paying at all in the actual border rank. Yeah, so this states now the new terms that we add are kind of boring because it's just a scalar multiplication, but it brings omega down. OK, and now we can apply the very same construction. Exactly, everything is the same. We don't have this problem with f and g being different. F and g are going to be the same here. So
satisfy the first one. These are your basic triples, the 6 triples there.
yeah.
They don't satisfy this condition that the sum is equal.
No, why? 0 plus 1 plus 1 is 2, and 2 plus 0 plus 0 is also 2. Yeah, that's how we chose the indices. Yeah. So in the same way that we added these guys, we can also add lots more of them. Like you can add 3, 0, 0, and 4, 0, 0, and exactly the same way if you actually look at the identity. But this is not going to help because this is not tight. And if you think about it, then you can see that it also can't help when you do the construction. So that's why it's important for this to be tight. So now we have to choose some distribution pi. So now pi is generally of this form alpha over 3, alpha over 3, alpha over 3, beta over 3, beta over 3, beta over 3. Okay. Now what is the value of p? So we have to look at the projection of this thing into the first coordinate. So the projection of pi into the first coordinate, which I'll denote by pi x, is, let's see if we can do it. So how many zeros do we get? So we get alpha over 3 plus 2 beta over 3 zeros. And we get 2 alpha over 3 ones, and beta over 3 twos. Okay, so that means that p is going to be roughly 2 to the n, the entropy of pi x. Okay, now the asymptotic sum inequality is going to give us, so we have this p, and now what is the volume of each of the tensors here? So we have alpha over 3, well, we have an alpha fraction of tensors of cubic volume q over, yeah, volume q, and the rest of volume 1. So in total, we get this cube volume of q to the n alpha over 3. And this is most q plus 2 to the n. Okay, now if you take the n through, then you get, and you divide by n. Yeah, if you take the n through, then you get 2 to the h of pi x times q to the alpha over 3 is at most q plus 2. Okay, and now we have to optimize over both q and this alpha. So beta and alpha sum to 1, so there's only one variable here. And next hour, we'll explain how to do this optimization. In this case, it's not so difficult. So I think the best value of q here is 6, and the best value of alpha, I think, is like 0.952 or something. And that's how you get this bound 2.387. Okay, and the next hour, we'll see how to milk this identity even more. The same identity. So all the developments in the past 27 years have been with this very identity. So you can look at it and admire it. And very fruitful. Okay, so now let's take a 5-minute break.
באיזשהו מובן היתרון של קיו גדול הוא מינורי כיחס פחות או יותר 3. כן. אז זה כאילו מיניתם פחות או יותר פונקציה לינארית. באמת זה לא ברור, אולי כולם שתולים פחות או יותר חוץ ממטה. כן, זה מפתיע. איכשהו ציפיתי שיותר גדול יעזור. אבל לא, פה ברור שיש עוד אופטימיזציה.
כן, כן. כן.
ברור שאתה רוצה לבחור יותר מהגדולים, כי שם אתה מרוויח ואפשר.
כן, כן.
להשתמש
לא, ברור, אבל אם...
קיבלת 3 כפלים בחינם, אז אתה רוצה שהם יהיו משמעותיים.
כן, אבל... אני לא... So I asked Olga to ask Bini to find out where these identities come from. So we'll get an answer, hopefully, within a few days. I don't know. I don't remember what they write in their paper in the beginning. Maybe it had been known, appeared previously.
So it's not computer generated.
No, you did it by hand.
Although you know, now people look with computers.
So what did they do with computers?
You'll see the next hour is exactly on this issue.
This was,
Yeah, no,
this is
that's
not,
by hand.
the identities are not.
No.
Algebraists are discovering identities all the time for various purposes.
Oh, I guess they tried several stuff, but
No, but I think there was some intuition.
yeah, of course. Just wonder where they.
So you can see there's more of them. There's this number 4, which I'm not going to go into. This was the original identity in the paper where Strassen does this laser method.
Is there a new method?
Oh, yeah. So you have to borrow from someone. They only printed 12. I think these guys have lots of them.
יודע, לא ברור.
לא, ומי שהגיע בסמסטר השני. לא, בשבוע הבא לא נהיה.
פשוט אתה, זה עכשיו, צריך להיות צער, אתה בכל אופן התכוונת להסביר לי פרטים, שתוכל להסביר לי הכל בשבוע הבא.
כן, מתי אתה טס?
אמרתי לך אז,
אבי, מתי אתה טס?
אתה גם טס,
כן.
אנחנו באותה טיסה.
אני לא יודע. כי הם רצו לתת לי טיסה מוקדמת ולא הסכמתי.
מה?
הם רצו לתת לי טיסה ב9 בבוקר או משהו, ואמרתי להם שזה מוקדם מדי.
אני אגיד לך תכף להסתכל.
זה שאתה מקל, זה אומר שאני יכול לגמור את כל הזמן.
כן, זה לא רק זה, אתה יכול להזמין כולם ללאנץ'. לא, זה צחק, זה קשור.
טוב, נמשיך. Okay, so let's go on. Okay, so what did we do so far? So we had this identity with the sum of matrix multiplication tensors that wasn't disjoint. So we took a high tensor power and we zeroed some of the variables, and now everything that remained was disjoint. And now we use the asymptotic sum inequality. So what can we do better? So here's the idea. So again, we take this identity and we take a high tensor power and we zero some variables and we get some disjoint matrix multiplication tensors. But now before applying the asymptotic sum inequality, there may be a way of merging some of these tensors into larger matrix multiplication tensors. And they're worth more to us. Okay, and that's how we can get even more, but you can see we're not going to get much more, probably, which is why these improvements are not very good. So this is the idea.
So is there any indication that this process can stop? The matrices are large enough, can't you get tensor plots and reduce?
So that will be open question number 2. Yeah, I think there should be a way to analyze this construction from the get-go instead of taking higher powers. And this will answer this question, but I don't know.
But even without this combination, it's not clear that there is no inequality that gives 2.
Right, yeah, that's a good point. So last week I mentioned that if you're only applying the asymptotic sum inequality once, then you can't possibly get 2 because there's always a way of improving it. But here that's not what we're doing. Here we're taking a higher and higher tensor power. So it could be that there is some magic identity that does give you omega equals 2.
No, but I even meant in the sense of approaching 2. There is no reason that applying the asymptotic sum inequality once to the right inequality will not give omega equals 2.
No, we know that that can't happen.
No, well, omega below any constant.
So you will need many identities if you want to get. So for each given identity, you can't get 2.
Yeah.
So yeah. But here it could be that you do get 2.
I see. Good, yeah.
Yeah, because you're applying it for many n. Yeah. Yeah. Well, we will keep this. Yeah. So this general idea is kind of.
Related to this and related to what you asked us to do
Uh-huh.
before, did anybody study whether this family of inequalities has some structure, or they, they obey some general form that,
What do you mean?
you look at the warm-up inequality and the main identity, warm-up identity and the main identity. Are they related in any way? Are they
Yeah.
bound?
Yeah, so well, you take the warm-up identity and you add some more factors, some more terms. No, so if you zero out the new terms in the second one, you get the first one. So it's just an optimization.
Yeah, but there are other identities you don't know that they are. So specific.
So more generally, you can ask about the variety of tensors of border rank at most something. And nowadays, for small numbers, you can actually compute the variety. So in principle, you can, yeah.
You can know them all.
You can know them all, yeah. But the varieties are very big. This is also new. This is a paper by Landsberg and al. From like a few months ago. Okay. So because we don't really know how to do this idea, how to make this idea work, taking high tensor power and then merging things, we're going to do it in 2 stages. First, we're going to take a small tensor power and do some merging, and then we're going to repeat the same construction. Okay, so that will be the idea. So of course, the smallest power, which is not 1, is 2. So that's why we square the basic identity, and we do some merging. Okay, so when you square the basic identity, then what you get is, so you get here 36 terms. This is most q plus 2 squared. So it's a really big mess, and now it's going to be even messier. So now let's look at one of the terms. So it's 1, 1q, 0, 1, 1. Is that okay? Yeah, so this is one of the terms, and we can write this. This is the same as 1, 1q squared, 0, 0, 1, 1, 1, 1. Now, in view of applying the same machinery, so what this machinery needs, it needs a list of basic triples with indices, which is tight. So you can see that this 0, 0, this is not an integer. So we need to somehow come up with a rule of converting these index vectors of length 2 into integers, which always sum to the same value. So the most natural way of doing this is just taking the sum. Yeah, so this is going to be the new group 0. Yeah. Yeah. So now we're breaking up each variable group into 4 parts. 0, 0, 0, 1, well, even more parts, into several different parts, so more than 3. And these parts are indexed by vectors of length 2 of integers. But in order to apply this construction, say in order to take this inner product, then you need to have integers. Yeah, so you need to come up with some scheme of converting these indices of length 2 into, and this scheme has to be tight. So here the idea is you just take the sum of the indices, and this guarantees that the sum of the new indices is always exactly 4.
But then you'll have to rule out either 0, 1 or 1, 0.
No, so what's going to...
Not confuse them.
Yeah, so we are going to confuse them, and this is actually good for us because this is how we merge tensors. Yeah, so that's a good point. So there are 2 more factors here that get the same 0, 2, 2 indexing. So it's the 1, 1, 1, 0, 2, 0, and 1, 1, 1, 0, 0, 2. And the other guy, which is the same with okay, so and we have to treat them all together because when we do the zeroing, then we really need well, the basic triples to be distinct. Okay, so what happens is we have these 3 terms, and now we have to somehow merge them together. But luckily for us, if we take the sum of all this, then I claim that this is some other matrix, some multiplication tensor, which is of this form. Okay, since what's happening here? So here we have some large inner product of size q squared, and it's summing these y and z variables to the variable x 0, 0. Yeah, and here we have another inner product of length 1, and again it's summing something to the same variable, the same accumulator, x 0, 0. And the same here. It's the x 0, 0 is the recipient. So we can just merge them. Okay, and now what Coppersmith-Winograd did was go over all the 36 factors and do this process. And you can see why we need computers to do it for higher powers, because it gets some combinatorial explosion. So this is in the end note. You can see, well, 3 types of terms which are nice when we do this merging. And in the end, there is some mess. So when we do, yeah. So what is the mess? So if we look at what lands at 112, then we get this. So I'll only copy the result. Okay, so this is what I call the T4, or what they call T4. And this is where this merging process wasn't so helpful. So we didn't merge anything, and much worse, this is not a matrix multiplication tensor. So the indices here are not disjoint. So now if we try to apply the same machinery, we will get stuck at the end, because we won't be able to apply the asymptotic sum inequality, right? Because it can only handle matrix multiplication tensors. So now the idea is to generalize the asymptotic sum inequality. So what's happening here? So we're going to take this high tensor power, and we zero some variables, and in the end we're going to get some lots of copies of let's say kn copies of something which looks like it's going to be some n for some n times this T4 to some power L, and the rotation of T4 to some power L, and another rotation of T4 to the power L. So this T4, it appears also in rotations, because the original identity was rotation invariant. So for rotation, I use this letter rho. So it rotates the x, y, and z indices. Okay, so after zeroing, we will get into this situation. So we have kn copies of disjoint copies of this mass. And now what we're going to do is we're going to concentrate on this factor, and we're going to zero some variables so that this does break up into disjoint matrix multiplication tensors. And then we can apply the asymptotic sum inequality. Okay, so this will be the idea. And to formalize this idea, then I'm going to describe a notion of value, which is how valuable a tensor is for exactly this process. Okay, so the value of a tensor. So we start with the easy case, where T is rotation invariant. So this example is unfortunately not rotation invariant. But so in this case, we define the value of
Sorry, what's the rotation?
yeah, a rotation. We take the x, y, z indices, and we
Permutation.
yeah yeah
Okay, cyclic permutation. Or
Yeah.
any permutation.
no, here it's a specific cyclic permutation, and if you only look at the indices, then it looks like a rotation. So the value is going to depend in general on some parameter alpha, which you can think of as a candidate for omega. Okay, and there's been an extra parameter t. So this is the maximum of ni, mi, pi to the power alpha over 3 for all ways of zeroing variables in t to the n to get this big disjoint sum of ni, mi, pi tensors. Okay, so I'm taking our tensor and taking the nth tensor power, and now I allow you to zero variables, and I want whatever remains to be disjoint matrix multiplication tensors. And now I'm interested in this quantity. And this is basically the quantity that interests us in the asymptotic sum inequality. So I want you to maximize this. Okay, and we'll see later how to calculate this. And we already actually know how to calculate this, basically. So now we define the value of the tensor. This is the limit as n tends to infinity of this thing. Okay, so now if you're very pedantic, you can ask, but how do we know that it tends to a limit? So don't worry, and it tends to a limit. So you can show it's super multiplicative and everything's fine. So this is the value of the tensor in the case where t is rotation invariant. And when it's not rotation invariant, then we're going to symmetrize it. And this is the same way that we got, see if it's still here. So when we got the bound, we started with the bound on symmetric multiplication tensors, n and n, and then we wanted to get the bound on n and p, so we symmetrized. Now we're going to do exactly the same thing. So for general tensors T, you define S is a symmetrized tensor. And then the value is just the cube root of the value of S. Okay, so now you have the definition. We won't worry so much about this case of general tensors, although this is what we actually need here. So what does this notion of value give us? Where does it come from? So the basic thing is so that's properties of the value. Yeah, so if the value alpha of a tensor is at least the Bode rank of a tensor, then omega is at most alpha. Yes, this is the basic property of the value. This is how we defined it. And this is really just the asymptotic sum inequality rephrased. Okay, so to prove this, we take a high tensor power, and we zero variables, and we use the asymptotic sum inequality. Okay, so this is property 1, and property 2 is the asymptotic sum inequality itself. So we have a sum of, if the sum of the alpha of ti is greater than this thing, sum, right? Then omega is at most alpha. We're not going to prove this, but the proof is surprisingly easy. You just show that the value is super additive and super multiplicative. Okay, so this is, yeah. Oh, right, and the third property, which is important, so we already know this. Yeah, so it's basically a generalization of volume, of the cube root of volume. Okay, and now I'm going to show you how to estimate the volume of a general tensor, assuming that it comes with a set of basic triples which is tight and rotation invariant. And we already know how to do this because this is exactly this half of the board. Yeah, but before doing that, so maybe take another look at the tensor T4.
This value is only defined for matrix multiplication tensors?
No. For matrix multiplication tensors, we don't need the notion of value. So we're going to use the value to handle this T4. Yeah, so in order to apply this machinery that is in the other half board, I will need to, so we know what the basic triples are, but they need to be tight. So how do I come up with a set of tight basic triples here? So the idea is very simple. So we know that if we sum each two indices here, we get exactly the same thing, right? So these two sum to 1, these two sum to 1, these two sum to 2. And also, they all sum to 4. So if I look only at the first index, And you can see that on the one hand, it has to sum to 2. And on the other hand, if two indices are disjoint, then they actually correspond to disjoint variables. If two indices are different, then they actually correspond to disjoint variables. This is because the sum is constant. Okay, so this is going to be the set of basic triples. Okay, so now we're going to...
The basic triples are those that individual coordinates are.
no, so it's going to be this 1, 1, 0, 0, 0, 2, 1, 0, 1, 0, 1, 1. And each of them is going to be worth something else for you. Okay, so now I'm going to describe how to compute the value using this machinery. Come on. Just use another one. Okay, so computing the value. Okay, so
Computing the volume or just putting a lower bound on it? Maybe
right. So in general, it's actually lower bounding the value. But in some cases, you can actually get the actual value because you also have an upper bound. Yeah, so the idea is, well, to take a high tensor power and to 0 variables to get this thing. So in this case, the constituent tensors are matrix multiplication tensors. But more generally, there can be other tensors whose value is already known. But for simplicity, we'll only consider this case. So, well, the idea is just to run this construction. Okay, so for each source distribution pi, and now I'm first assuming T is rotation invariant. So
it's not one.
is rotation invariant?
It's not one.
No, we first assume that T is rotation invariant, and yeah. So for each source distribution pi, we have these f pi, fp, and g. Yeah, and we can compute them. So we get the same kn, which is roughly equal to f over g times p. So the value is at least this kn, or the limit kn to the 1 over n times the, so here you can think about it, this V as the volume of an actual matrix multiplication tensor, but in general it will also work for arbitrary tensors. So for each basic triple, we need to take the value of this triple and times pi I many times. Okay, so what's happening here? So we have done to, no, the entropy is going to come up here.
Oh, pi of n, so.
Yeah. So what's happening here? We try to compute the, so this thing is going to be a lower bound on V alpha n of t. So we get this many copies of something, and this something is worth this much to us. So you can think of it that in this case, these TIs, the constituent tensors, are just matrix multiplication tensors. So this is just a definition of value. More generally, they can be more complicated, and then you have to substitute value, and just everything works. But here you can just think of it as matrix multiplication tensors. Yeah, so T was the sum of TI. Okay, so this is the lower bound that we get from this construction. So
is kn roughly this number, right? Is this work? No, the number, the f over g times p.
Oh.
This is yeah. This was for this kind of line. Oh, this was for.
yeah, this was in general. Whenever you had the basic triples were rotation invariant and tight, then
Oh, these numbers depend on.
yeah, it depends on, yeah. So now we're going to estimate, we're going to calculate this quantity, kn to the power of 1 over n. Okay? So, right, so what is f? F is roughly 2 to the n times h of phi. Right? And p is roughly 2 to the n times h of pi x. So pi x is the projection into the x indices. Okay, and what is g? So g is the sum over all distributions sigma that have the same asymmetric distribution sigma that have the same x distribution and y distribution and z distribution. But here, because everything is rotation invariant, we only need this thing. So it's the sum of 2 to the n h of sigma x. Now, because this sum doesn't contain so many terms, it contains only polynomially many terms, because there are only polynomially many distributions for each given n, you can estimate this by the max. So it's roughly the max over all sigma, such that sigma x is equal to pi x of 2 to the n h of sigma x. Okay, and now we can put everything together, and we get a nice formula.
All this notation is from the legal paper. Already appears in Coppersmith.
So, yeah, I think it's already in the Coppersmith-Winograd paper, only they didn't have the PF and G because in their case, F was equal to G. Yeah. So what we get is that, so if you look at the log of this lower bound that we get on the value, so this is at least what? So it's at least, well, we'll divide by n. So it's at least h of phi, well, h of phi x plus h of phi minus the maximum sigma such that sigma x is equal to pi x of h of sigma plus sum over I of pi I times the log of the value of Ti. Yeah, so now I did some algebra. If you take the logarithm and you divide by n, then you get this nice formula. So this is what we want to maximize. This is the lower bound we get on the.
This is the entropy of sigma, not of sigma x.
Yeah, yeah. It's entropy of.
The evaluation of T rho.
Oh, sorry. Right. Right. And we also have an upper bound. The upper bound is like this. So the upper bound is on the maximum over all pi. And here it's at least the maximum over all pi. Yeah, so in general, they only present lower bound on the value, but actually when you don't have this f versus g business, then this is tight. Yeah. Okay. Yeah, so any questions about these formulas? Where do they come from? What do they say to us? What do they tell us? So this formula first appears in François Legal's paper, and if you look 2 years back, it's in my lecture notes. Okay, so now the plan is clear. So now we want to calculate the value of T4. So we just compute somehow we do this optimization and find the optimal pi and get this value.
It's not rotation invariant. We have to
Oh, sorry, right. So in general, when it's non-rotation invariant, then there is something you need to do. But I won't worry with the details. So basically what you would like to do is you would like to take this distribution on T, and then you want to take its own tensor product with its rotation of itself to get the distribution on S. And then when you do this, and it almost works out, you don't get this factor. So you have to modify slightly the combinatorial construction, and then you get this, even for general tensors. Right. This is all in the lecture notes. Yeah, so you can run this process for T4, and you get something. We can actually write it like there's a formula, but all we need to do is for a given alpha, we need to know what the value is. And then we're going to do some binary search on alpha. So for any given alpha, this is just some optimization problem that you can solve, and I'll explain how in a minute. And then you get some lower bound on the value of T4. And then you do the same thing for the identity squared, and you get some lower bound on the value. If the value is at least k plus 2 squared, then you got an upper bound on omega. So now you do binary search, and you get the best bound that you can do on omega.
What's the value for alpha chosen to begin with?
So for a matrix multiplication tensor, the value is just this NMP to the alpha over 3. And in general, you use this formula. Yeah, and this formula is not necessarily tight. It's probably tight, but it was open question number 1. So it may be possible to get slightly better bound than omega if you tighten the construction, if you think it's not tight. Yeah, and if you do all this, then you get this 2.375 something that was the best known for 20-something years. Okay, so now I'm going to tell you how to evaluate how to do this optimization, and then how to generalize this to higher powers. Okay, so how do we do the optimization? So we will start by understanding this condition. So this is the difficult part. So when is, rather, given pi, when is sigma x equal pi x, sigma y equal pi I, y, sigma z equal pi z. So you can write it as a linear system. So you take the sum of all triples such that the x index of I is equal to some x. Then you need that the sum of sigma I minus phi of I is equal to 0. So this is for all x indices x. So here it's in the basic triples, so it's like 0, 1, 2. And you do the same for y, and the same for z. And you also need that this sigma is a probability distribution. Okay, so we get some linear system of equations that we denote by V. And now the easy case is when V doesn't have any non-trivial solutions. Right. So easy case, it's when V has only trivial solutions. So then we have an actual formula for the value of the tensor. Let's say just equal to maximum over pi of h of pi x plus the sum of I, phi of I, v alpha of ti. Okay, and so this function h is, entropy function is concave. So this is a convex optimization problem, and you can solve it using your favorite algorithm. Here you're optimizing over the simplex, and there's a special algorithm that works just over the simplex. It takes like I don't know, take 50 C lines. It's very simple. So this is the easy case, and this is all Coppersmith-Winograd had to do. Of course, they didn't do it this way. They did it like this. But it's possible to do it this way. This is the way you should do it. The general case, when V has non-trivial solutions, it's a big mess, and no one knows how to actually solve the general optimization problem. So instead, you get good lower bounds. And there are two methods. So one method, which came later, is by Legal. So general case. So there's method A, it's Legal's method. So what is the idea in Legal's method? So we first solve this optimization problem, right? And we find the best pi. And then we compute this minus term, this sigma. Yeah, so you compute pi ignoring sigma, and then compute sigma. Okay, and this gives some feasible solution. And now computing pi, as we said, this is a convex optimization. Computing sigma is convex optimization. This is very easy. So using this method, which is much better than the other method in terms of complexity, then he was able to do the 16th and 32nd power. Earlier, there's the Stothers / Slevska-Williams method. And then the idea is to assume, to add as a constraint that pi equals sigma. Okay, now if you look at Virginia Williams' paper, then you can see that this pi is called, I think, Aleph, and this sigma is called Aleph prime. And somewhere hidden in the line, there's this assumption that they're equal. And nowhere is it mentioned that you don't have to make this assumption. But fortunately, now we have Legal's paper, and we know everything. Okay, so if we use Lagrange multipliers, then we can actually see what this condition entails. So use Lagrange multipliers. So it means that the gradient of the entropy of pi has to be in V perp. Yeah, and it's the same as we need that log of pi I is in V perp. Okay, so this is a new constraint. And under this constraint, we still have to only solve this problem. So this is, again, some convex optimization. But for some reason, this constraint makes things really messy, and it's much harder to solve this constraint. But you can get explicit solutions this way. This is a nice thing. And this is what Coppersmith-Winograd actually did.
So what is one better than the other always?
So empirically, this method seems to be a bit better. And you can see the exact numbers in.
But there is no.
No.
You don't know that one is better than the other in general.
No, I don't think so. And you can think, like, if you wanted just to improve omega, then you can do some better optimization and get 10th digit better this way by solving a better relaxation.
When you are in case one,
Yeah.
when is it that there has only trivial solution and
Yeah. So you can check that if all your indices are 0, 1, 2, 3, then you're always f equals g. Always the solution is trivial. And in my lecture notes, then there's an example with 0, 1, 2, 3, 4, where you do have this mess. And it's kind of messy, so it's on page 7. You can look at it offline. Yeah, but unfortunately, it does happen when you take higher powers. So when you go to the 4th power, then it actually happens. Okay, so now the only thing I have to tell you is what is this mess with the higher powers and what happens there. Now you can evaluate for yourself how big of a breakthrough are these papers by Stothers, Virginia Williams, and Legal. Yeah, so that's those higher powers. Okay, so the idea is to just repeat the same construction. So we took this basic identity and we squared it, and then we squished it together, and then we got these, well, we merged some of the tensors, and some of the tensors got messy, but we could calculate their value using this, solving this optimization problem. So we just do exactly the same. So you do exactly the same. Okay, when you do it, and you find out that tensors of type 0 something and something always merge to matrix multiplication tensors. Okay, so this is where you gain. And in the Virginia Williams paper, there's a formula for the value of for the dimensions of these tensors. And for in the other cases, then you don't get anything nice, but the constituent tensors, you already calculated their value in the previous step, so before you were squaring this identity. So you can run the construction, everything is nice. So this is the idea. Yeah, some people tried. You can also do this in an asymmetric way. Say you take the tensor square, and now you tensor it with the basic identity. So now you get the cube. Now you can still do everything, but you don't get any improvement. And this is sort of not clear why not. It so happens. So that's why people take powers of 2. And you can see this breakthrough of Legal that got, I think, better in the 5th digit or something by using this technique A instead of technique B. He could, the computer could work harder for him. And if you have a cluster, then you can probably get the 64th power and get further improvement and so on. But where this headed? So now we have open question number 2. So now take the limit of this construction. Can you say something about the limit without going into this mess? Maybe, especially because we know that the only metric of tensors is really of this type. So you can imagine that there's something smarter that you can do. Of course, this is not going to lead to a big improvement because we see that the improvements are converging, but this will, at the very least, explain what the limit of this method is. So this is open question number 2. And open question number 3 is find a better basic identity to start with. Yeah. So any questions about this?
The basic identity, you mean the sum inequality?
No. This is the Coppersmith-Winograd identity number 2 in your handout, which is all that has been used since 87. Yeah. No new identities since 87. There have been new ideas. There's this group theory method, but so far they haven't gotten us anywhere. Something which may be more relevant in this paper about coherent configurations, they define a different problem where you still want to calculate something which is like the matrix multiplication tensor, but you're allowed to have arbitrary coefficients. So you want to have the same support, but you can have arbitrary coefficients. And you can define the exponent in this sense, and of course, it can only be better than the matrix multiplication exponent. But they show that if the new exponent is 2, then it implies that the matrix multiplication exponent is also 2, because they have some reduction. So if you only want to prove that omega equals 2, then you can solve this easier problem, where you can add coefficients. So this is another thing which people can try. But it's probably only worthwhile if you actually get omega equals 2, because otherwise the bound deteriorates very fast in this reduction. So this is maybe the one new idea that is actually relevant to get new bounds. Any more questions?
If we are in the question period already, so you'll get only one hand. So this all assumes that we are looking at 3-dimensional tensor, which is indeed the basic matrix multiplication,
Yeah.
which comes from multiplying 2 matrices. You can look at, I don't know if anybody tried, I mean,
I don't.
You can do the whole thing on 4, right?
That's true. So I don't know if anything breaks with the trilinear algorithms part. Yeah, probably not.
No, that's
Yeah.
But the sum inequality, would that be true also for?
We just repeat the proof.
It's the same. Everything seems to be the same. Only
yeah.
you'll have the 4 tuples.
Yeah. Yeah.
And maybe they.
Yeah. So it would be kind of weird if you got anything better, because you can.
There's more room for this combinatorics.
Yeah. No, that's true. That's
I have
true.
no idea. Intuitively, you think that you should just multiply 2 matrices, but maybe just these views, naturally generalize.
Yeah, that's true. I don't think anyone tried to do anything like that.
There isn't a well-defined notion of tensor multiplication, right?
So there's an algebra of tensors, and then tensor multiplication is this tensor multiplication, and the also sum is the disjoint sum. So there's this.
Eddie has a different.
Yeah, there's this tensor algebra which was defined by Strassen and probably appears in like a dozen different names, where addition is disjoint sum and multiplication is this tensor product.
But it's not the same thing as matrix multiplication.
No, it's not the same.
No.
It doesn't say the dimensions change.
The
Yeah,
dimensions,
yeah.
So because the only reason I asked is that it's conceivable that if there was a suitable notion of tensor multiplication, there's a better hope of achieving the actual exponent.
So
Yeah.
Eddie had, well, before you came, Eddie gave a lecture.
But in the case we investigate, these are mostly hypermatrices, because it's not independent of the basis. The advantage here of the ranking is that it's completely depends on your choice of basis.
No, that's right. It could be that you could find some other problem and you can get better one just because it's a different problem.
So I have a philosophical question. So you went into the trouble of learning all this. So what would you pay for improving the third digit? I mean, that's your goal? Or
No,
of
no.
course, understanding the combinatorics is interesting, but I think nobody has any indication that it's going to improve the third digit.
Yeah, so I agree. So, well, there are 2 nice combinatorial problems. These were open questions 1 and 2, but the really interesting part is open question 3, which is find a way to find better identities. The rest, I still think it's interesting, and it might be part of the way of showing that this new identity gives omega equals 2. So it's still relevant, but yeah, to get an actual improvement, you need to either do something completely different or just find a better identity.
More questions?
Yeah.
Absolutely no lower bound that is
So we have the expert here on lower bounds, and
For the case of bounded coefficients, if you are not allowed in your arithmetic circuit to use algebra, it's illegal. Just coefficients will say up to the value 1, then run as an n squared log n over. So the exponent is still 2, but it's safe.
yeah, and sometimes this sort of bounds you can prove them algebraically, and for example, you can show that f of t is optimal in some sense. Even in the case of rectangular matrix multiplication, the best bound is n squared log squared n. So I don't think anyone expects, even if omega equals 2, then you probably get like n squared pi log n if you do everything correctly.